Hello everyone. We will continue in the series of videos related to the chapter Electric Charges and Fields, and today we will be discussing about the units of charge and the principle of superposition of electrostatic forces. Units of charge. Now the SI unit of charge is Coulomb. All of you know that the SI unit of charge is Coulomb, and we can write Coulomb by capital C. All of you know this, we can write Coulomb by capital C. Now suppose Q1 is equal to Q2 is equal to Q. We will find out how to define 1 Coulomb. Now we know that the relation for Coulomb's law is F is equal to K, which is the electrostatic force constant, Q1 into Q2 upon R square, right? So if Q1 is equal to Q2 is equal to Q, and R is equal to 1 meter, and F is equal to 9 into 10 to the power of 9 Newton. Why we are talking about this? Because the value of K, the electrostatic force constant, the value of K is equal to 9 into 10 to the power of 9 Newton meter square upon Coulomb square. So we say that if Q1 is equal to Q2 is equal to Q, and R is equal to 1 meter, and F is equal to 9 into 10 to the power of 9 Newton, and if we substitute all these things in our equation for Coulomb's law, we will get F is equal to 9 into 10 to the power of 9, which we have written here. The value of K, as I told you just now, earlier also in my previous video I had told you, that is the value of K is 9 into 10 to the power of 9. Q1 is equal to Q2, which we have considered as Q, so it becomes Q into Q, and R is equal to 1 meter. So this 9 into 10 to the power of 9 and 9 into 10 to the power of 9 gets cancelled, and you are left with Q square is equal to 1, which is nothing but the value, the Q can be plus minus 1. That means it can be a positive or a negative charge. Okay, so 1 Coulomb of charge, if we have to define 1 Coulomb of charge, we can define it is that much of charge which when placed in vacuum, because the value of K, you know, we had done it in the previous video, it is 1 upon 4 pi epsilon naught, and epsilon naught is relative, epsilon naught is electrical, absolute electrical permittivity of free space. So the charges are in free space which we are talking about. So 1 Coulomb is that much charge which when placed in vacuum at a distance of 1 meter, because we took R is equal to 1 meter, from an equal and similar charge, because Q1 is equal to Q2 is equal to Q, they would repel it with a force which is equal to 9 into 10 to the power of 9 Newton. So this is how we define 1 Coulomb of charge. It is that much charge which when placed in vacuum at a distance of 1 meter from an equal and similar charge would repel it with a force of 9 into 10 to the power of 9 Newton. Okay, I hope you have understood. Then the CGS unit of charge, the SI unit of charge is Coulomb, and the CGS unit of charge is given by stat Coulomb. It is given by stat Coulomb, right? It is STAT stat Coulomb. As charge on an electron is 4.8 into 10 to the power of minus 10 stat Coulomb. Now you know charge on an electron in terms of SI system of units, it is equal to 1.6 into 10 to the power of minus 19 Coulomb. But in CGS system of unit, the charge on an electron is 4.8 into 10 to the power of minus 10 stat Coulomb. So electron charge in terms of SI system of units, it's 1.6 into 10 to the power of minus 19 Coulomb, and in CGS system of units, the charge on the electron is 4.8 into 10 to the power of minus 10 stat Coulomb. That's how we write it down, stat Coulomb. There is no abbreviation for this, you have to write it down in this manner only, stat Coulomb. Okay, so therefore if you want to find out the relation between the SI unit of charge and the CGS unit of charge, which is stat coulomb, it comes out to be 1 coulomb is equal to 3 into 10 to the power of 9 stat coulomb. If you want to find out that relation, then it comes out to be 1 coulomb is equal to 3 into 10 to the power of 9 stat coulomb, and you can do it from here only, because in SI system it is 1.6 into 10 to the power of minus 19, and in CGS system it is 4.8 into 10 to the power of minus 10. So how much is 1 coulomb? You can get it. It is 3 into 10 to the power of 9 stat coulomb. Okay. Now we'll move further. Now we talk about principle of superposition, right? Principle of superposition of electrostatic forces. So we'll talk about this. Now Coulomb's law was giving us the mutual electrical force between two charges. When we discussed the Coulomb's law, these are the two charges Q1 and Q2 separated by a distance r. So it gave us the force between the two charges which are at a certain distance from each other, and the relation all of you are now familiar with. F is equal to K Q1 Q2 upon R square, right? Okay, where K is the electrostatic force constant. This is the mutual electric force between two charges. But in case if we have more than two charges, then the principle of superposition is used in order to find out the force on a particular charge in addition to Coulomb's law. So when we have to calculate the force on a charge due to several stationary charges, there is a charge, let's say Q0 here, but there are several other stationary charges, Q1 here, Q2 here, Q3 here. Let's say there are n number of charges and Qn is somewhere here, right? So when we have to calculate the force on a charge, that is Q0, due to all these charges Q1, Q2, Q3, Q4, then we have to use what is called principle of superposition is used in addition to Coulomb's law, right? Coulomb's law will give us a force in between two charges, and principle of superposition will help us to calculate the total force on the charge Q0 due to all other charges which are in its vicinity. According to superposition principle, now what is the statement of the principle? This gives us the statement of the principle. According to superposition principle, total force on any charge due to a number of other charges at rest is the vector sum of all the forces on that charge due to other charges taken one at a time. So when we have to use the superposition principle, what we do is we take one particular charge Q1 at a time and find out what is the force on the charge Q0 due to this particular charge Q1. That is, what is the total force between the two charges, okay? And then we will write that particular relation. Similarly, we will find out what is the total force, what is the force on the charge Q0 due to the charge Q2 and Q3 and so on, one by one. And then we will find out the total force, and that will be given by the vector sum of all the forces on that charge due to the other charges taken one at a time. So we are taking each charge one by one, and we are finding out what is the force on the charge Q0 due to Q1 and then due to Q2 and so on. Then we find out the vector sum of all these forces, right? Of all the forces on that particular charge. Now when we are talking about the vector sum and we are finding out the when we are finding out the force on an individual charge, that is when I am finding out the force due to Q1 on Q0, the presence of these charges, that is Q2, Q3 and so on, is totally not in consideration. It is the force due to individual charges. This is what the statement says: the force due to individual charges are unaffected due to the presence of other charges. So if Q2, Q3, Q4, Qn are all present, but when we are finding out the force on Q0 due to Q1, the presence of all the other charges is not it doesn't have any effect on the force due to Q1 on Q0. Okay, so this is the principle of superposition. It's also called principle of superposition of electrostatic forces, right? Now we will try to understand this principle of superposition of electrostatic forces. Okay, so in order to understand the principle of superposition of electrostatic forces, what we can do is, we have this particular diagram on the in this particular slide, and you can see over here that suppose the point charges Q1, Q2, Q3, Qn. Let's change the yes, suppose point charges Q1, Q2, Q3, Qn are there, right? So this is our coordinate system x, y, z, and the charges are the charge which is, let us say, the test charge on which we are trying to find out the total force is Q0, it is placed here, and the other charges Q1, Q2, right, and Q3, they are placed very close to, let's say, Q0, right, and these are the position vector of Q1 is R1 vector. All of you know what is the position vector. It's the vector of that particular charge Q1 with respect to the origin. So similarly, the vector R2 is this particular vector, that's a position vector, R3 and Rn. So let's say there are n number of charges, but we are not showing all the n number of charges, we are just showing a few charges in our particular diagram, and we are trying to explain it that Q1, Q2, Q3 are some charges which are at position vectors R1 vector, R2 vector, R3 vector from the test charge, and the test charge is Q0, right? So in this particular coordinate system, so what is the total force according to the superposition principle, which we have just understood in the previous slide? So according to the superposition principle, the total force on the test charge F0 is said to be the test charge, right? So this F0, the total force, it is equal to F01 vector. That is, what is, how do we read this? It is the force on Q0 due to Q1. It is the force on Q0 due to Q1. Similarly, the force on Q0 due to Q2, right? So that is written as F02 vector, and so on. We have n number of charges which we have considered. So therefore the charge, the nth charge, that is the Qn charge, will have a force F0n on the test charge Q0, right? So you can see now over here how will the direction of the force Q01 will be taken into consideration. So this test Q0 is said to be the test charge. Test charge is considered to be a positive charge, right? And Q1 also we are considering it to be a positive charge. So what will be the direction of F01 vector? It will be a repulsive force, so it will be directed in this particular manner. So F01 vector, that is the force on Q0 due to Q1. So that is F01 vector. Similarly, the force on Q0 due to Q2, it is given by F02 vector, and the force on Q0 due to Q3, it is given by F03 vector, right? So total you can see over here, F01 vector is this, F02 vector is force on Q0 due to Q2, and so on. F0n vector, it will be the force on Q0 due to Qn. Now how do we write out, according to the Coulomb's law, which we have already stated, how do we write down the force on Q0 due to Q1? So that force can be written as F01 vector, it is equal to 1 upon 4 pi epsilon naught, the two charges are Q1 and Q0, upon R1 naught square. What is R1 naught? R1 naught will be the unit vector directed from Q1 to Q0, right? So R1 naught square into R1 naught cap. We are writing it down in the vector form, so therefore we have written it down in this particular manner. So this is the force on Q0 due to Q1, even though other charges are also present, as the principle of superposition states that the presence of other charges does not affect the force which we are calculating on the charge Q0 due to Q1. Okay. So we continue from here, we move further. Similarly, the force on Q0 due to Q2, even when other charges are present, is given by F02 vector is equal to 1 upon 4 pi epsilon naught Q0 Q2 upon R2 naught square into R2 naught cap and so on. And similarly, F naught n vector will be 1 upon 4 pi epsilon naught Q naught Qn upon R square n naught into R cap n naught. Now, what is the total force? In the previous slide I had told you what is the total force. Total force is equal to F naught vector is equal to F naught 1 vector plus F naught 2 vector and so on till F naught n vector, when we have considered that there are n number of charges. So therefore, when we talk about this, the total force will be equal to this. How do we write it down? You know, 1 upon 4 pi epsilon naught is common, so we have taken it outside and we have put the bracket and we write Q naught Q1 because this is Q naught Q1. Okay. Q naught Q1 upon R1 naught square into R1 naught cap. So therefore, we have this Q naught Q1 upon R1 naught square into R1 naught cap, this expression. Similarly, plus what is F naught 2 vector, we can write this over here, right? We write this whole thing in F naught 2 vector and so on. F naught 3 vector will be this and plus so on, continuation, plus F naught n vector will be equal to this. So F naught vector, which is equal to 1 upon 4 pi epsilon naught, we can write it down in the summation form. Summation of I is equal to 1 to n Q naught into Qi upon Ri naught square into Ri naught cap. So when I put I is equal to 1, I get this expression, the first one. When I put I is equal to 2, I get this and so on. So therefore, when we put the summation, we have found out the combined expression for this particular F naught. And similarly, F naught vector, because Q naught is also common, so that can also be taken outside over here and we can write Q naught upon 4 pi epsilon naught summation of I is equal to 1 to n Qi upon R cube Ri naught cube into Ri naught vector. Now, how have we written this? Because we know that Ri naught, R cap I naught, right? R cap I naught is equal to R I naught vector upon the magnitude of R I naught, right? So when this is the definition of unit vector. Definition of unit vector is vector upon the magnitude of vector. So the magnitude of vector is Ri naught, vector is I naught vector. Therefore, when I write that down, so in the denominator I'll have one more Ri naught along with Ri naught square, I'll have one more magnitude of Ri naught. Therefore, I get Ri naught cube into Ri naught vector. I hope you have understood this expression also. And similarly, we can write this Ri naught can be written as Ri naught vector. Ri naught vector can be written as R naught vector minus Ri vector. This is also in the vector form only, we have written it down, and therefore the expression becomes Q naught upon 4 pi epsilon naught summation of I is equal to 1 to n Qi upon R naught vector minus R naught Ri vector. Magnitude of that, it is cube of this, so therefore we have written this into Ri naught vector, therefore R naught vector minus Ri vector. So this is principle of superposition, right, which is principle of superposition. Hope you have understood this principle of superposition. And now we move further and talk about what is dielectric constant or relative electrical permittivity. Dielectric constant is also called relative electrical permittivity. So we have already talked about what is the force between two charges when the two charges are placed in vacuum and they are at a certain distance. We have written down the expression due to Coulomb, due to the Coulomb's law, right? And according to the Coulomb's law, the expression is F naught is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R square. Now the same two charges Q1 and Q2, right? The same two charges, these are Q1, this is Q2, separated by a distance r, this is in vacuum, right? Now suppose the same two charges are in a particular medium, right? The same two charges Q1 Q2 separated by the same distance are in a particular medium. Then how do we write down the expression? We now put for medium we write Fm is equal to 1 upon 4 pi epsilon. We will write this as epsilon. This is what is called absolute electrical permittivity of the medium. It's called absolute electrical permittivity of the medium, right? Okay. So we write it down like this of the medium. So Fm is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R square. Same two charges separated by the same distance. Now dividing this is, let's say, expression 1 and this is expression 2, dividing 1 by 2, which we have done. F naught by Fm, if we write it down, we get epsilon upon epsilon naught. So if we do that, we get F naught upon Fm, we get is equal to epsilon upon epsilon naught, right? Which is equal to epsilon r is equal to k, where k, this k is called relative electrical permittivity of the medium, and it is also called dielectric constant. Both words, both are used for it. Epsilon r is called relative electrical permittivity of the medium. It is also denoted by k, which is also called dielectric constant of the medium. It is also denoted by k and it is called the dielectric constant of the medium. So this is how we can write down the expression for dielectric constant k, or which is also called relative electrical permittivity of the medium, relative electrical permittivity of the medium, right? So therefore dielectric constant of the medium can be defined as, now we can have two definitions of dielectric constant, one in terms of permittivities and another in terms of forces, because epsilon upon epsilon naught, one in terms of this and one in terms of F naught upon Fm, that is in terms of forces. So the first definition, this is the first definition for dielectric constant, which is the definition in terms of permittivities. So dielectric constant of the medium can be defined as the ratio of the absolute electrical permittivity of the medium to the absolute electrical permittivity of free space, because epsilon r, or which is equal to k, which is equal to epsilon upon epsilon naught. So it is equal to this, right? And another definition is in terms of the forces, which is we can define it in terms of this forces, and it is defined as the ratio of the force of interaction between 2 point charges separated by a certain distance in free space or vacuum, because F naught is the forces between two charges at a certain distance in vacuum or free space to the force of interaction between the same 2 point charges. Same 2 point charges, as I told you earlier, same 2 point charges held at the same distance apart in a particular medium. Held at the same distance apart in a particular medium. So we get two definitions of dielectric constant, one in terms of permittivities and one in terms of the forces between the two charges, right? Thank you. Hope you have understood. If you want to see more such videos, please hit the subscribe button and like and share the